Alright students, in the previous videos we have studied the growth and decay, real life problems, solve it mathematically and by using the techniques of differential equation, and then solve the growth and decay of anything like radioactive decay, that contains how radium decomposes or disintegrates with respect to time, and also the bacterial growth, and bacterial growth is in a certain culture, how it grows, and also the population growth fits into that example. Okay, now we are modeling a change in the temperature with respect to time. So for that we have to know about the Newton's law of cooling. Newton's law of cooling, right? So this law says that the temperature of the body changes at the rate, that means at the rate means with respect to time, and the change means what is the change? Rate of change, derivative. So instantaneous rate of change is the basic definition of derivative. So that says the temperature of the body changes at a rate, that means dt by if it is temperature, then temperature change with time, d of temperature divided by dt, t is time. That is proportional to proportionality, that is proportional to the difference in the temperature. Difference means subtraction. So to the difference in the temperature between the surrounding medium and the temperature of the body itself. So one side is, let T is the temperature of the body and Tm is the temperature of the surrounding medium. So the temperature of the body changes at a rate, that means dt, temperature of the body divided by dt, that is time, and that is directly proportional to the difference of temperature, in the temperature between the surrounding medium and the body itself. So difference between the temperature of the body and the temperature of the surrounding medium. So that is the Newton's law of cooling, right? So I am converting this proportionality into a constant, into an equation that becomes constant of proportionality T minus Tm. So this is our model, and we have to find the solution of this model, and then we solve the problem, a specific problem, and that is given in the coming next these statements. So okay, example is a container of the boiling water. Boiling water is at 100 degrees centigrade, as you know that. So a container, here the body is the container, right? Or water, container in water in a container. A container of the boiling water, that is, boiling water has a temperature 100 degrees centigrade already, is removed from the fire. So that means initially it is a boiling water, and allowed to cool at a 20 degree room temperature. Now our room temperature is, surrounding medium is 20 degrees centigrade. So when a container of the boiling water, initially it was a boiling water, and then if it is kept in the room temperature, that is 20 degrees centigrade. If after 2 minutes, so that is change in the time, if after 2 minutes the temperature of the water in the container is 80 degrees centigrade. So that means initially it was 100 degrees centigrade, and after 2 minutes its temperature is reduced due to the effect of that surrounding medium. Its temperature is reduced to 80 degrees centigrade. So that means it's reduced, decreased. So find what you have to find First of all, we will answer these questions, but first of all we have to construct a model and solve this model. So our model is dt by dt small t is equal to k t minus tm. Here Tm is 20 degrees centigrade, surrounding medium, right? And it contains the initial condition that if it is removed from the boiling water, so initially, okay, I am writing this here, subject to, first initial condition is capital T is temperature, so it is a function of time. So T of at time 0, it was initially temperature was 100 degrees centigrade, and after 2 minutes the temperature of the water in the container is 80 degrees centigrade. So when time is 2 minutes, it is reduced to this. Now we model the problem and find the constants with the help of this. Okay, I am replacing this 20 t minus 20, and to solve this it is separable, so I am using 1 over t minus 20, cross multiplying it into dt equals to k into dt, and applying the integration on both sides. Its integral is, it is 1 by some function into derivative of that function. So derivative of capital D is 1. So that means it is natural log of t minus 20 equals to k into t plus c. Okay, and then we apply t minus 20 equals to e to the power k into t plus c. So same procedure, e to the power k into t into e to the power c, t minus 20 equals to that, we can say it is a c1, so c1 e to the power k into t, and solution is c1 e to the power k into t plus 20. So this is the general solution of Newton's law of cooling. Now we are applying the initial condition and basically initial condition and boundary condition. So okay, I am doing it in the next page so that you can understand it. So our solution is T equals to e to the c1 e to the power k into t into c1 plus 20 surrounding medium. So this is the solution, and these two are conditions. Applying this condition, I am mentioning this as equation A. So apply this condition this CA to equation A. So T is 100, capital T, temperature is 100 when time is 0. C1 e to the power k into 0 plus 20. 100 equals to C1 e to the power 0 is 1 plus 20, and C1 equals to 100 minus 20, so C1 is 80. Okay, Next condition is when time is 2 minutes. Here time is in minutes. Okay, so when it is 2 minutes, then temperature is 80. So apply condition B to equation A. Okay, I am replacing here in equation A the value of C1. So T is 80 e to the power k into T plus 20. Okay, T equals to, T is after 2 minutes, T is 80 degrees centigrade. Okay, so T is 80 degrees centigrade and it is 80 e to the power k and T is 2 plus 20. So 80 minus 20, 80 e to the power 2 into k. 60 divided by 80 equals to e to the power 2k. So 60 by 80 is 1 by 4, not 1 by 4, it's 6 by 8. So it is almost 3 by 4 equals to e to the power 2k. So natural log of 3 by 4 equals to 2k, or k is 1 by 2 natural log of 3 by 4. So this is the value of k, and in calculator calculate it and tell me what is the value of k. Alright, the value of k is minus 0.144. Okay, now replacing the value of k in this equation, so T here is 80 e to the power minus 0.144 T plus 20. So that is the basic solution of this problem, specific problem. So this I can say it's equation B. Now we can apply and answer the further questions of this example. Okay, so first question is find the time. So here that means answer A is time. We have to find the time it will take the water to be at 40 degrees centigrade. So that means that we have temperature is 40 degrees centigrade and you have to tell the time. So 40 in this equation, 40 equals to 80 e to the power minus 144 T plus 20. So this is basic calculation. 40 minus 20 divided by 80 equals to e to the power 0.14 T. So 40 minus 20 is 20. 20 by 80 equals to e to the power minus 0.144 T. So 1 by 4, 20 by 80, and when we apply log on both sides, natural log, I'm doing it step by step so that you can thoroughly understand each step. So it becomes like this, and this becomes 0.144 T, and this is natural log of 0.25, that is 1 by 4. So natural log of 0.25 divided by minus 0.144 equals to t. So time is, after solving calculator, using the calculator, the time is, solve it and then tell me. Yes, time is 9.6 minutes. So this is solved. Okay, now we come to the next question, and that is, second is find. Okay, part B is find temperature of the water after 5 minutes. So here we have to find the temperature and the time is 5 minutes. So in this model, in this solution, we have to find, time is here 5 minutes and we have to find the temperature. So replacing in equation B, time is should be replaced 5 and we have to find the temperature. So T equals to 80 e to the power minus 0.144 into T plus 20. So calculate it and solve it. Sorry, T is 5 here. I'm writing it into 5 plus 20. So calculate it and tell me the answer. So temperature is 59 degree centigrade. So these two are the answers of that specific problem. So your problem is now finished. If you have any queries, you can ask me and discuss it with me in the online lecture or in the online discussion. Okay, thank you so much all of you, and best wishes.